Let's be honest, naming acids can feel like you're trying to learn some kind of secret chemical language, right? It just seems designed to be confusing. But what if I told you there's a really simple key that unlocks the whole thing?
I mean, come on. You've got nitric acid, nitrous acid, sulfuric, sulfurous, and then, just to keep you on your toes, hydrochloric acid gets thrown into the mix. They all sound so alike, but they're completely different chemicals. It's a super common stumbling block, but today we are going to clear it up for good.
Okay, here it is, our secret weapon. Now, this is going to sound a little silly, but this one sentence is pretty much the master key to naming the vast majority of common acids. I took a bite and it was delicious, so I ate the whole thing and got sick. Go ahead, say it out loud. Burn it into your brain, because you're about to see just how powerful it is. So this deliciously sick mnemonic, as I like to call it, is our way into a huge family of acids known as oxoacids. And just like the name sounds, these are the acids that contain oxygen. This one little phrase is going to handle almost all of them. So what exactly is an oxoacid? Well, it's way simpler than it sounds. It's just an acid that has three things: hydrogen, which is what makes it an acid in the first place, oxygen, and at least one other element. You know, things you've seen before, like nitric acid, HNO3, or sulfuric acid, H2SO4. You see the H, you see the O, and you see something else. That's an oxoacid. And here is where the magic happens. Our mnemonic breaks down into a super simple rule. It all comes down to the name of the polyatomic ion, you know, the anion that's inside the acid. If that anion's name ends in "ite," just like in bite, the acid name will end in "ois," from delicious. And if the anion name ends in "ate," like ate, then the acid name gets the ending "ic," from sick. That's it. That's the whole core rule right there. Okay, let's put it into practice with some real-world examples. Take a look at the nitrate ion, NO3-. It ends in ATE, so the acid it forms is nitric acid. Now, what about the nitrite ion, NO2-? It ends in ITE, so its acid becomes nitrous acid. See how that works? The exact same pattern holds true for sulfate and sulfite, which becomes sulfuric and sulfurous acid. It's kind of wild how that one goofy sentence just cracks the code. Okay, so that's great for pairs of acids. But chemistry likes to throw curveballs, right? So what happens when you have an element, like chlorine, that can form more than just two kinds of oxoacids? Well, our ite and ate rule is still the foundation, but we just need to add one more layer to our system: prefixes. The easiest way is to think of it like a ladder of oxygen atoms. Our regular us and ic acids that we just learned, they're the middle rungs. Now, if you have an acid with even fewer oxygens than the us one, you add the prefix hypo, which means under or less. And if you have one with even more oxygens than the ic acid, you add the prefix per, which kind of comes from hyper, meaning above or more. And this is where it all just clicks together so perfectly. Let's take a look at the whole chlorine family of acids. Chlorite gives us chlorous acid. Chlorate gives us chloric acid. That's our core rule. So the one with the fewest oxygens, hypochlorite, becomes, you guessed it, hypochlorous acid. And the one with the most oxygens, perchlorate, becomes perchloric acid. It's a beautiful logical system once you see it laid out. All right, deep breath. We have totally mastered acids with oxygen. But what about the ones that don't have any oxygen at all, like good old HCl? Well, for these, we have a completely different rule. And thankfully, it's even easier. These guys are called binary acids. Binary just means two parts. You've got hydrogen and one other non-metal element. The most important detail here, the big red flag you're always looking for, is there is absolutely no oxygen. When you see an acid formula with just an H and one other symbol, you know you're in binary acid land. And you are going to love how simple this rule is. You just take the prefix hydro, tack on the root of that other element's name, and then finish it all off with iic acid. So here's the key takeaway. If you see or hear the prefix hydro at the beginning of an acid's name, that is your giant signal that there is no oxygen in that molecule. Now here's a really important little detail that trips a lot of people up. The compound HCl, when it's just a pure gas, is actually called hydrogen chloride. It only earns the fancy name hydrochloric acid when it's dissolved in water. We show that with this little AQ symbol, which stands for aqueous. It's the water that kind of unlocks its acid powers, and that's what gives it its acid name. So let's pull all this together. You now have a complete toolkit. Seriously, with just two main paths to choose from, you can confidently name pretty much any common inorganic acid that gets thrown your way. It really just boils down to asking one simple question. Does the acid have oxygen? If the answer is yes, it's an oxoacid, and you pull out that mnemonic. Remember, what you bite is delicious and what you ate makes you sick. If the answer is no, it's a binary acid, and you use that hydro prefix. That's the whole system. Right, you ready? Time to test out your new skills. You walk into the lab, you see a bottle with this formula on it, H2SAQ. Take a second. Run it through that mental flowchart. What do you call it? And the answer is hydrosulfuric acid. Did you get it? Let's walk it through. Step 1. Is there oxygen? Nope. So we know we use rule 2. We grab the prefix hydro, we take the root of the element, which is sulfur, and we slap on the ending ic acid. Boom. Hydrosulfuric acid. Simple as that. So there you have it. You've cracked the code. You now know how to name these acids. But this really leads to a much deeper, much cooler question, doesn't it? Why? Why does adding or removing a single oxygen atom completely change the naming rules, the structure, and even the strength of these compounds? Now that is where the real chemistry begins.